Welcome to the Agricultural Engineering Podcast YouTube channel. Today we are sharing with you a webinar, which is a presentation by Dr. Maharaj and Mr. Trevor Pike from GroundTruth, South Africa. The aim of this webinar is to highlight on the use of unmanned vessels for aquatic monitoring, and it will be focusing on integrated system, which includes unmanned aerial vehicles and Internet of Things enabled sensors. We hope that you will enjoy this informative session.
Okay, good afternoon, everyone. Welcome to this branch meetings renditions for the South African Institute of Agricultural Engineers. This is our second branch meeting for the year, and with the title of Innovative Aquatic Monitoring, Integrating Unmanned Aerial and Survey Vessels and Internet of Things for Water Quality, eFlows and Bathymetric Surveys. So quite a mouthful and a lot to be covered in a relatively short time. So I hope the speakers we've arranged for today are able to get quite an interesting concept across through to us, and maybe while not applicable to each and every single one of us, but the overarching concepts and learnings can be taken and applied in other areas of our work today. So let me just start off by introducing SAIAE. So for those who are not agricultural engineers and joining us from, well, maybe from other professions, disciplines, and even provinces, the South African Institute of Agricultural Engineers represents the discipline of agricultural engineering in South Africa. I'm proud to represent them, and we've been formally established since 1964. This is a voluntary association which is registered with the Engineering Council of South Africa, and it serves as a professional home for ag engineers, technicians, and technologists across the country. So it's also, we've got maybe not as big as the other voluntary organizations, but definitely sizable to foster and collaborate communications through other institutions as well. We also have a host of we host a lot of CPD courses throughout the year. We've had quite a number of interesting ones in the previous year. We've got an interesting one coming up on hydroponics course that's happening in September. And we obviously provide a lot of guidance to young members, creating relations between students and industry professionals, and provide a platform for members to address the issues that they feel strongly about. So just let's move on. So just in case we have members coming in from other provinces and you'd like to get in touch, just a slide to introduce all the relevant chairpersons for those provinces. And feel free to contact myself or Senzo after this meeting so we can help you to put you in touch with the relevant chairpersons for your provinces or areas of interest. Okay, let's move on to today's speakers and, well, basically why we're all gathered here this afternoon. So allow me to introduce the speakers we have today, all representatives from GroundTruth. Dr. Udhav Maharaj is an agricultural engineer that works with the GroundTruth team on the hydrodynamic modeling and digital innovation sectors. Mr. Trevor Pike, professional engineer, is an environmental engineer with many years of experience, and his areas of interest include hydraulic modeling and the design of nature-based solutions. And we're also joined by Kylie Farrell today, who's the senior ecologist and integrated water resources management specialist for GroundTruth. So Udhav and Trevor are going to dive into some exciting technology for aquatic monitoring. Think drones in the sky, unmanned boats, or USVs, and smart sensors all working together. So they'll show how this trio of data collection methods can collect detailed water data like temperature, turbidity, and depth, all mapped with very high precision. And hopefully by the end, we'll all get a clear picture of how these tools can improve water resource management and support environmental planning. But more importantly, how we can take these fourth industrial revolution technologies and marry them to get some meaningful insight and data to help us make more educated and learned decisions. And plus, it's a great way to stay on top of the latest innovations in monitoring technologies. So Together with Udhav, Trevor, and Kylie, they all work together on a variety of projects in the rural and urban environments. And for this presentation, they'll be speaking about some of the drone and river hydraulics work that they've done with the International Water Management Institute. Right, so if I can hand over to the GroundTruth team to present, please take over. And yeah, we'll reserve at least 5 minutes at the end of the presentation for Q&A. I'll hand over to the GroundTruth team. Udhav, thank you.
Yeah, thanks, Raj. So just to confirm, Trevor and I are on the same line. And yeah, we'll be starting the presentation now.
Right, just want to check if you guys can see that screen. Is it?
Yes, we can.
Presentation showing all right?
Yes, it is. Thank you.
Great. Yeah, well, thanks for the opportunity, and good to be able to share some of our work with you guys. I think, as you mentioned, the topic is quite a mouthful. But yeah, I mean, if you unpack it slightly, I mean, there's innovation, there's aquatic monitoring, there's aerial, unmanned aerial surveys. So that's basically drones. There's survey vessels, IoT, water quality, environmental flows, bathymetric surveys. So there's a whole bunch of stuff packed in here. And just reflecting on that a little bit as we were putting this presentation together, I just thought, well, you know, how do we actually get to this point? And at GroundTruth, just a little bit of how it kind of works here is that we are a multidisciplinary company, and yeah, civil engineers, agricultural engineers, hydrologists, but then also freshwater ecologists, wetland ecologists, social scientists, etc. So there's a whole bunch of cross-cutting themes at play at GroundTruth, and yeah, it's a privilege for us as engineers to be able to apply these various techniques into different spaces. So not just the engineering sector, but basically putting them into other sectors. And in this case, we're going to be chatting about the eFlows, environmental flow studies, and particularly around the hydraulic component. So just a very brief overview of the presentation. I'll be giving us a quick intro and a little bit of background on the hydraulic modeling. Udhav will be taking us through some the digital innovation stuff. And Kylie will be chatting through some interpretation of the results. So if we just get straight into it. So in terms of the hydraulics, so generally, it's really understanding the flow and movement of water. Generally, I mean, from an engineering point of view, it's generally along pipes and channels, irrigation canals, etc. In this application, we're looking at the movement of water specifically through rivers, and in terms of why it's important in the eFlows. So the eFlows or environmental water requirement studies, eFlows, environmental flow studies, reserve determinations. These studies go by various names, and maybe just a little bit of background to these studies. They are generally a requirement from the Department of Water Affairs, and it's really there as a voice for the environment. So really to understand, if you are issuing water use licenses for abstractions, for argument's sake, how much water can you take out of a system before you actually start compromising the health of the system, before the services that are provided start collapsing. And yeah, and the other side of the coin is how much water can you add to these systems before you also start compromising their health. And that obviously links to intubation transfers and also wastewater treatment works. So you're actually adding water to systems, and how does that actually affect the health of the systems. So really the hydraulics component allows us to get an understanding of the water levels. Critically, you have a whole bunch of stuff going on in rivers, fish and inverts being one of them. Various fish species prefer certain types of habitat, and that's really linked to your depth of flow and your velocities. So yellowfish, for argument's sake, like shallow, fast-moving water. Other fish prefer slower, deeper water. So it's really understanding, if you start fiddling around with the discharge in rivers, how does it actually start affecting the habitat for the different creatures that need that water to survive. Really just, we also mentioned, Sarge mentioned a little bit about the IWMR, so the International Water Management Institute project. We were fortunate enough to be involved in this project last year. We managed to get some funding just to look at some innovation around the eFlows and how we collect data, how we interpret that data, and how we can actually look at improving the confidence in those things. So at GroundTruth, we do run a full drone survey system here. So we run LiDAR imagery. We do a lot of work around water quality and also looking at particle image velocimetry, which Udhav will chat to later. Really a technique around measuring velocities of water from video footage. The output data from that, so basically being able to generate point cloud data for the bathymetry, so that below the water level and above the water level, that's using the LiDAR above, being able to stitch that data together using imagery, looking at the velocity and tying that into a hydraulic model, which then could generate these habitat distribution maps, and like I said, improving your confidence in your results. So that was the IMI project, which Udhav will touch on a bit later. So really the hydraulic modeling side of things, what we're wanting to do is to achieve and develop a relationship between your depth and your discharge in your river. Really it links largely around it's based on the Manning's equation. And really what we're wanting to do is from a stage discharge curve, measure a specific point. So you have a measured discharge and a measured depth. You do some modeling, you generate a curve, and then obviously with increased readings in field, you can improve the confidence of your curve. But basically, this will then link back to the various habitats of the fish, etc., that are in the river systems. So in terms of the hydraulics component, why do we need it? It's really, like I've mentioned, to inform the various specialist studies. And I must note that these eFlow, these ecological water requirement, the eFlow studies are very complex studies. So they're generally carried out by a bunch of specialists who go to field. So you have a fish specialist, an invert specialist, geomorphologist, somebody who looks at riparian vegetation, normally a hydrologist, and also a hydraulics person as well. So it's generally a team of about 4 or 5 people going into field. And the hydraulics really links, it's cross-cutting across all the themes. So basically understanding the effect that it has on the habitat for fish and inverts. From a geomorphology point of view, is understanding the energy of and velocities in your system to make sure that you do create sediment movement, that you make sure that you get enough energy in your system to actually roll those stones and cobbles over to create habitat for your inverts, to create breeding grounds for fish, to get that sediment moving. So you have to keep that into account as well. So you can't just put up a dam and it's for argument's sake, or take out a lot of water and drop your flows. Obviously your geomorph side of things is going to be compromised. And from a riparian vegetation as well, obviously your vegetation on your banks needs to be healthy to actually stabilize those banks to reduce erosion. So those banks need to be wet at certain times of the year to sustain that vegetation. And the hydraulics, once again, links into that in terms of looking at your depths. So all these various components are all kind of considered, and the EWR kind of program revolves around a workshop at the end where all these various specialists will basically come together and make sure that each of their components are satisfied. And like I say, the underlying theme through all of this really is the hydraulics component. So in terms of how we go about it, what we do first and foremost is to identify a suitable site. Like I said, it has to satisfy the various specialist requirements. So it has to be a site that has habitat for fish. It's good for vegetation. It provides habitat for your inverts, so your vegetation, your sands, your gravels, etc. And then what we do is we look for what we call a critical cross-section, or that allows for critical habitat. And the kind of the foundation of the eFlow study is to make sure that we try and find a worst case scenario cross-section in a river, so that we can understand the section obviously has to be highly sensitive to any changes in flow. And the idea and the thinking behind the eFlow study is that if you can satisfy your conditions for a very critical cross-sections, then the rest of the river systems should be satisfied. So we kind of try and look for that worst case scenario cross-section. run our models on that. In terms of choosing sites as well, we want to choose a good site. These are great sites in the photos, nice and straight sections of rivers, constant slopes. There's no obstacles in terms of bridges, roads, weirs, etc. Nice, even water surface, etc. So site selection normally takes quite a bit of time and basically has involvement from all the specialists. In terms of the data capture, date and time, importantly, especially if you're using discharge off a gauging weir, just to know what your flows are at the time. Steel pegs, all the normal GPS photographs. You have to survey a detailed cross-sectional profile, measure your slope per your river, and then measure your discharge if you don't have a gauging station close by. Typically, we use just a good old dumpy level and tape measure. This is really for the 1D cross-section, so just a single cross-section through your river. And up until the point of the IMI project, this is kind of what we were reliant on. And I think that this is where the innovation really has taken these studies ahead in leaps and bounds. So basically, what you do is set up your tape measure, survey your detailed cross-section, and these cross-sections are, when I say detailed, they're highly detailed. So you're basically surveying every rock, every little hole in the river along your cross-section at your tape. And obviously you need to understand your relationship between your areas and wetted perimeter, also your surface areas for your habitat for your inverts, etc. So they're very, very highly detailed cross-sections that take generally quite a long time to do. The other thing we have to do is measure your slope, and this really is just taking your surface water level and doing that at the time that you measure your discharge as well. Then obviously looking at telltale signs on your banks for high water marks, etc., so that you can actually look at your slopes when you come to your modeling of what your slope is doing for various flow scenarios. In terms of measuring discharge, generally an easy thing to do if you've got a standard cross-section, just obviously your velocity and your area. In a river situation, it's slightly different. Obviously you have to go about it slightly differently. The first thing you have to do is choose a correct cross-section, and you'll notice that the cross-sections here where we're measuring your discharge generally are not the same cross-section that you use for your critical cross-section. The reason being, your critical sections generally have a lot of riffle type of habitat, lots of stones, fast-moving water, eddies, etc. So try and find a good site with steady flows, and and basically make sure that you can get an accurate reading. Things to avoid, obviously, pools, slow-moving water, uneven bed, very fast-moving water, etc. Just in terms of the measurement, we basically just break up the cross-section into different segments, measuring the width across and the depth at various segments, and then working out the area of each segment. We then measure the velocity at each of those segments and get an average velocity per segment. And then simply just to work out the discharge is working out your area times your average velocity per segment, and then summing that up for your cross-section. What that feeds into is a model which basically gives us, this is one of the output charts from the model. So the abbreviations there, SVS, SS, etc. Those are the different habitat classes, and this is specifically just for the fish. So SVS stands for slow, very shallow, then slow, shallow, slow, deep, and then fast, very shallow, fast, intermediate, and fast, deep. So those are the 7 classes that are looked at when it comes to fish. And you can see on the x-axis how you can see how with different depth of flow, how the percentage area of each of those classes change. What's interesting, you can see here at around 0.5, meters deep, you can see some of this blue habitat that actually starts emerging. So that's your slow, deep habitat. What you can just imagine that if you obviously take out too much water in your system and you say drop to 0.3, you're losing all that habitat. And if you've got a specific fish species in the river system that is reliant on that slow, deep habitat, you're going to put that fish under pressure. And likewise, if you've got a fish that enjoys the fast deep, you can see fast deep is only activated at this cross section from 0.3 meters deep and above. So if you take out too much, you could potentially lose a lot of that habitat. So we generate these habitat kind of maps for the fish, for the inverts. The geomorph guys look at the velocities, and the veg guys look at depth of flows in the banks, etc. I think it's important to emphasize at this point as well that all this information is typically reliant on a single cross-section in the river. So you basically are making decisions on your eFlows based on a single cross-section, which is where we felt that it would be really good to innovate and actually look at it more at a reach level. And this is where the IMI project was really useful to us in terms of bringing in a bit of innovation. And looking at this at a little bit more holistic level. I think just up until this point in time, we haven't really had the technology to look at more than just cross sections and rivers when we're setting up these systems. But now we have the luxury of technology on our side, and we were able to play in that space. So I'm just going to hand over to Udhav now, who can chat us through a bit of innovation on that IMI project and how things have moved forward from the slides that I've shown you.
Okay, thanks, Trevor. Yeah, so maybe to just pick up on what Trevor was saying, initially the work was done around a single cross-section, and for this project, one of our focus areas was to see how can we improve our surveying methods, and then can we extend from a single 1D cross-section to a two-dimensional profile. So not only modifying how we collect the data, but how we actually use it. So in terms of the data collection, we looked at LiDAR, which is in essence a way to survey everything, your land profile, so terrestrial surveys. LiDAR does not penetrate through water. So to get the underwater depths, we had to look into echo sounding devices or sonar devices and GPRs. So that led us to trying to figure out what's the best combination of survey techniques to actually generate a full terrain or elevation model, so of your floodplain and your riverbed or your river profile. And then once that was done, we also needed to look at, can we actually use this full terrain model to model and represent those different habitat classes that Trevor showed on the previous graph. And in essence, what we found was that we can use the LiDAR surveys for terrestrial or above water surveys, couple that with RGB or high resolution imagery and multispectral surveys for investigating what happens to your vegetation. So that's your riparian vegetation. And then using either a sonar device or an echo sounder to do your underwater surveys, and then stitch that together to drive a full terrain model. So as in the next few slides, you'll see exactly what I mean. So it'll be a bit easier to picture what I'm talking about. So in terms of echo sounding bathymetry, there's a range of different types of sensors out there. And generally, they're not used with a drone. So another thing that we did was we had to develop a system that could be integrated with a drone so that the survey could be unmanned. Because as you can imagine, operating this little unmanned vessel here without a drone could be quite tricky, especially in fast-flowing deep waters with crocodiles or hippos or any dangerous creatures in the river. And so if you look at the image on the right, I'm just going to get a laser out here. But if you look on the right, there's okay, I can't get the laser, but anyway, this the survey vessel on the right is generally operated manually. So for a single cross section, the survey vessel moves up and down, and you collect data. What we did was we found an echo sounder, and then we retrofitted it with a GPS unit and used it to survey at a ping rate similar to a drone. So we collect a point cloud, and then in essence, what you can do is then generate a profile of anything underwater. So it would look like this profile on the bottom left here. So this is the GTE Explorer, which is our unmanned survey vessel. On it, you can connect either echo sounder or a sonar device. We also added in turbidity sensor, temperature probes, and TDS, so total dissolved solid sensors. So simultaneously, water quality and depth parameters can be collected. And because it's operated with the drone, you can collect data not only for a single cross section, but for an entire reach of a river system. So here, what you can see on the right is the drone actually using a drone to actually pull the boat across the river system. And yeah, in essence, during a flight like that, we collect echo sounded or sonar data, which is the underwater points. And this was not done in the drone area before. So if you wanted to do an underwater drone survey, you'd either use a GPR device where you'd have to fly very close to the water surface, which is not the safest thing to do, or you could use very expensive LiDAR surveys. But yeah, coupling your sonar and LiDAR together was quite a new thing which we investigated. And then what we found was that this is suited to not only your bathymetric surveys, but you can also use it to do multiple surveys and get data on your sediment in your channel or your water body. And what we found was that this was much more efficient than a traditional survey. So you can imagine setting up a dumpy level, going across a cross section, and you get in one cross section for your river profile. With this device, you can survey your entire reach much more safely and efficiently. And the data that we collected was found to be suitable to be integrated with the LiDAR data. So that's your terrestrial data to form a complete elevation model. So yeah, maybe before I go into the elevation models, I'll just quickly speak about the water quality monitoring. So here you can see this is a piece of river, so it's an entire stretch where we collected total dissolved solid and turbidity data, and this was all collected with the drone and the unmanned survey vessel. And you can see here this helped having this sort of data. You're not only getting your water quality data at a single point, you can see how that changes across your river reach, which is quite useful because if you look at this picture here, there's a little cut-in on the left bank of the river, so where the cursor is, and you can see there your total dissolved solids and turbidity actually increases. So this was just to add on to the project. It wasn't a key thing to actually inform the eFlows, but it was a useful outcome from this project. In terms of the bathymetric mapping, I think now things would start becoming a bit more clear because if you look here on this top left, you can see a high resolution image of the same river system. On the right of that, you'll see a traditional terrain model where if you pull a cross section through the river here, it will be flat because your LiDAR data does not penetrate your water. So if you look at the bottom, so the colorful image here, you can see the elevation that we collected from the echo sounder that we used for the survey. And then we then stitched the echo sounder data to the LiDAR data, and we generated this topo bathymetric map on the top right, which is the full river profile. So you can see it's everything above land and below the water's surface. And you can even see that little cut-in on the right that I was speaking about earlier. And then below that is just an example of a single cross-section that you can pull from the model if you need to. So if you look at this blue line here on the cross-section, if we didn't have the echo sounder or sonar data, your cross-section would look flat like that because LiDAR does not penetrate water. So that's where stitching the two data sets becomes important. This is just another example of the Olifants River. So it's in Kruger National Park. This is a stretch of river that we surveyed, and you can see again the level of detail that you can get when you stitch your above ground and underwater profile for a river. So you can see when Kylie speaks a bit later on, you'll see how this becomes helpful. And yeah, this is just a comparison. So like Trevor was saying, we go very detailed normally. So if you look at the blue line, that's your total station cross-section. You can see there's quite a few points along your cross-section. So this is for the Olifants River. And if you look at the gray line, which is the data that we pull from the terrain model, so it's just one single cross-section, you can see that you pick up a lot more detail. And overall, the correlation is good with your total station data. So between your survey points, you are picking up a little bit more variation with this your digital terrain model that's generated with the two data sets. So just a quick recap, this is what Trevor was speaking about earlier. So you can see this is how your habitat classes look for a single cross-section. And these are your descriptors if you wanted to look at them in more detail. But what we then did was we looked at, can we actually use those descriptors for a 2D model? So these are just traditional 2D models where you can see, or you can model how your velocity and depth change over time. So what we did was we went into a normal 2D model and we modified that to include your habitat classes, which was also not done before with the specific 2D model that we used for the project. So yeah, this is an example of the 2D model now with your habitat classes. So you can see here as your flow dynamics change in the river profile, you can see how those habitat classes actually change. And when Kylie takes over, she'll explain the significance of this. But just to emphasize, this is now for a 2D level. So not just a single cross section, you can see it across the entire reach. And all of this is generated using the data from a drone and the unmanned survey vessel. Okay, so now I'd like to hand over to Kylie to explain. Oh, sorry, maybe one last thing. From the study, we also looked at how we can take it a step further. So something that we're working on now is actually looking at estimating discharge and velocity. So velocity, discharge, and depth using a survey vessel and a drone. And yeah, we call this the virtual weir concept. But this is where particle image velocimetry comes into play, where we actually track movement down the river profile, convert that into a velocity, and now you can see you get velocity calculated across your entire river profile, and then you can also get your average velocity. But yeah, now I'd like to hand over to Kylie.
Thanks, Udhav. Thanks, Trev. So how we use these 1D, 2D profile and all the modeling when it comes to the ecological side of things is we use it to set the ecological water requirements within these reserve determinations that we've been doing for the Department of Water and Sanitation. And I'm going to take you through a case study. This particular one is on the upper orange, and the pictures that you see in front of you is at a site just upstream from the confluence of the Orange and the Vole. And this was such an interesting reserve determination, as the first time we went to the site, we did the 1D profile. So it's just one cross-section across the river reach, informing the specialists of the different type of habitats, different type of velocity depths, classes for the inverts, for the fish, for the riparian and geomorphology. And so, these are the drone photos of the site and just showing you where the site is. Sorry, I'm not manning the presentation. Udhav, if you can just point where the site is on the little map, and then, the driver components at the site being the hydrology, the geomorphology, and then the responses being our diatoms, which is these microscopic algae that provide supplementary information to ecological water quality. Other responses being fish, invertebrates, and the riparian vegetation. And as Trevor mentioned at the beginning of the presentation, is we have all these different components, team of 4 or 5 specialists within these criteria, going and undertaking these surveys, obtaining the data that they need, trying to assess different habitats at the site. We come back, we run our own ecological models, so we understand what that present ecological state is at the site. And then we sit in a workshop together after the 1D modeling or 2D modeling gets done. The hydrologists, hydrolicians, and the ecologists sits together. And that's where we start to have a look at what were the results from the hydraulic survey and the modeling in order to identify how to set these ecological water requirements for the rivers. And it's such an important decision. And that's where the 2D model comes in. It provides us with a much higher confidence in our decision making, because we really only get one chance to do this, particularly in reserve determinations for the department before it gets gazetted. And as we stand with the National Water Act not being promulgated yet, there is so many outdated reserves that's been done more than 10 years ago. So we know that when this gets gazetted, it's going to be in cement for the next 10 years. So the higher the confidence results, the better. Can you go to the next slide, please, Udhav? So at this upper orange site, initially we went and did the 1D. And when we sat and we did the workshop, we were actually quite stumped because, as Trevor mentioned, selecting that site is extremely important. It's trying to find the perfect site for the ecological components and for the hydrolicians. So we like areas where there's a diversity of habitats, where there's riffles, stones, riparian vegetation, inundated vegetation, some pools, some slow-moving water. So there's a diversity of those habitat classes. But when the hydrolicians come in and they're doing the 1D, they need to make sure it's a straight river, part of the river reach. It's not sloped, can't be straight after a weir or any other type of obstacle. So sometimes we just can't find that perfect site. And that example happened at this particular site where the 1D survey was done along the pool upstream, but there wasn't any of that critical habitat from a fish or an invertebrate perspective. And we surveyed further down where there were the riffles, but it wasn't a good site for the 1D because it was a bit too braided and there were side channels, etc., which is not a good site for the 1D profile. So trying to establish that ecological water requirement was quite tricky because the 1D was more along a gravel and muddy substrate. So then we went back to the department and we said, we need to go back to the site and can we try this 2D profiling? And they were quite excited. It was the very first time that DWS have done the 2D hydraulic modeling before. And so we went back to the site and we did a 2D hydraulic survey of the entire reach. And I'll show you some maps shortly. So there we didn't need to worry too much about it being totally straight, or there were some channels on the side. The 2D encompassed all those different types of habitat classes that the ecologists needed in order to help make our decisions when we're looking at the EWRs. So it's a novel approach, and we were really excited to present this to DWS. Next slide. So as you can see, as a result of that 2D modeling, the image on your left, that's the photogrammetry survey that was undertaken at the site. And that's where they used to generate the high resolution imagery of the site and elevation data of the riverbanks. And then the image on your right is the bathymetric survey, where they used the sonar device that Udhav took you through, that's attached to the unmanned vessel. And then these two data sets of the elevation data they processed and they then stitched together to generate this elevation model. Next slide. So we're going to show you how it all works. And this is when we are all sitting in a workshop. So you can see, just to give you some context to this image, this is now the 2D model. And it's going to show us with the difference in velocities, difference in depths, it provides us different percentages of the habitat velocity depth classes. And as you can see, Udhav, if you go to the top part, the upstream, the most upstream part of this, which is further down, bring your cursor down, all the way down to the BS. So where Udhav's cursor is, that's where we had our 1D initial profile. Whereas the ecologists were working here where the channels are, because that's where the critical habitat was, as you can see right in the middle of the reach, yes. That's where there was quite a bit of braiding, side channels, some islands, so not suitable for 1D, but and that's why we're motivated for this 2D, because it's now encompassed that critical habitat for the ecologists as well. And what was so fascinating is when we push play on this, we can start to see from an ecological side of things is when those side channels are starting to improve in their different types of habitats. When is the fast, deep habitat coming? When are the critical habitats becoming exposed? So the water is not going over the rocky riffles, and we obviously need the water to be going over it, particularly for the invertebrates. As Trevor mentioned, the fish, some fish species, particularly the yellowfish in this reach, they love the fast shallow and the fast deep channels. So we're trying to identify, in order to set that ecological water quality, where is it most suitable in terms of the habitats from a biotic perspective. If you go to the next slide, we've actually pinned 3 images together. Right. So this is what we see. The image on your left is just showing us the different depth classes. You can see the darker the blue, the deeper it is. So the dark blue is around 2 meters. And this is at 65 cubic per second. So the discharge at 65. Because this generally starts off with the hydrologists. We say, right, we want to try and aim for a category C. And in our language, that means moderately modified, the system. So the invertebrates, the fish, the geomorphology, riparian, water quality is all moderately modified within the system just because of all the other anthropogenic impacts. Water quality, the flow is modified. It's very, with the upstream Gariep and Van der Klook dams, the base flows are constant. There's not enough floods and freshets. They've been altered. So it's a very artificial system from a flow perspective. So for us, we start off saying, what happens if there's 30 cubics coming through the system? How's the habitats going to react to that? And so the hydrolation will plug in 30 cubic meters per second into her model. And then we see, is it too little water? Is there hardly any deep channels, or are these side channels lying high and dry? The middle picture is showing us the different fish habitat classes. So again, it's those color blocks there that's our key for those fish habitat classes, as well as the percentage. So that's also quite a nice key from the 2D modeling, is if we say, right, let's up the discharge to about 65 cubic meters, what is our habitat classes responding to? And if you see the maroon is our fast deep, that's the dominant class, 61% of that full reach, including some fast deep habitats along those side channels, which is great because we want the fish to be moving up those channels. So it's a bit of a play with the discharges to see what flow is going to meet the needs of the fish and the macroinvertebrates. It's all about how they respond to that flow and what's adequate enough for them. Because as Trevor said at the beginning, a reserve, it's like a bucket of water. How much water do we need to keep in that river to meet our ecological needs? So our fish, our inverts, water quality, our riparian vegetation, and how much of that water do we need to meet the basic human needs? So the community is reliant on that river. And then whatever is left in the river, that is what can be used or sourced from the agricultural sector or industry or mining for water use licenses, abstraction, etc. So that's the importance of trying to play with these discharges. And at 65 cubics, the ecologists are happy. We feel at that discharge, the velocities are correct, the depth classes are meeting the needs of the fish, being the fast deep. And then the third image is showing our invertebrate habitat classes. Now, we've got a lot more different type of classes for the insects. Even though they're these small little critters, they're telling us a very big story about what is happening within the river channel. And there we are dealing with very fast coarse substrate, which includes fast flowing water, more than about 0.6 meters per second in velocity. And it includes your rocky habitats, your rocks, your cobbles, your boulders. Then we get your slow coarse substrate. So it's slow flow over that coarse material. And we get very fast fine substrate, and that is our gravels, our sand, and our mud. Dependent on which of the different velocities, fast or slow, over that type of substrate. So you can see there's quite a lot of different classes. But again, we are having a look in that side channel, knowing that's where we work, that's where the critical habitat was. And again, when are those channels filling up? When am I going to start meeting the needs for those fast-flowing dependent macroinvertebrates? So I'm going to be looking for much higher habitat availability when it comes to fast course and very fast course, which is our purple and our light blue. So I'm at least seeing my purple in that channel and a little bit of light blue in the other channel. So, as from an invert perspective, I'm happy that it's going to meet the needs for those particular indicated species at that particular discharge. I just want to add something before we go to the next slide. So it helps us to determine those ecological water requirements, or the eFlows, that are then eventually gazetted and promulgated. But what we're finding these 2D models are also helping us with is we've been working in catchments just recently, the lower orange catchment. The GroundTruth team were there doing the 2D modeling at Fieldsdrift and Senderlingsdrift. Highly complex systems, massive systems, and they've got their issue with the black fly larvae. And I'm sure you all are aware of it from the agricultural sector and whatnot, that these little black flies, when they start to pupate, around August, September, they formed this horrendous outbreak, a terrestrial outbreak, and they caused havoc with the farmers in the Lower Orange system and parts of the Eastern Cape along the Great Fish as well. And these little flies, and they go and sit on the eyes and their ears, and they feed off their blood and causes sores, and they scratch themselves basically to death. And the farmers lose a lot of revenue from these black fly outbreaks. So what we're going to try now, we're going to be having our workshop at the beginning of October, is to try and use the 2D modeling and see how to manipulate these flows within these systems where the flow is so manipulated from dams, from interbasin transfers, where the base flows are they're constant because they're not getting the floods and the freshets that these systems so desperately need. And that's the perfect condition for these black flies. So we want to use this model to see how we can perhaps in September time drop the flows right down to expose the critical habitat, so as off to kill off the black fly larvae, because they obviously need flowing water over the cobble that they love to sit on. The moment we can drop that flow, drop the velocity, they will start to die off, and then they obviously won't pupate and cause these big outbreaks. So that's something we're quite excited to use this model for, to manipulate flows and to try and control the pupation and outbreaks of these horrible macroinvertebrates that actually cause quite a negative impact on the socioeconomic components. Next slide. Sorry, and then just before Trevor and Udhav close off, so we don't only use these 2Ds for the ecological water requirement quantifications and setting rules for the rivers from an ecological perspective. What we also use them for is we take the HAB flow from the models that are generated from Udhav, and we put it into our ecological model. It's called a fish invertebrate flow habitat assessment model. And we bring in those different flow velocities, average and maximum depths, the various habitat percentages available for those velocity depth classes for the fish and the invertebrates. And then we select indicator fish and indicator invertebrates that only respond to flow, fast flowing, because we know that, if we're in the Lower Orange, for example, where we know it's a yellow fish and it's a great tourist area, and we start to reduce the flow, those yellow fish are going to respond immediately, and it could damage that population. And then what we do is we use that HAB flow and we run our model to assess the consequences from an ecological perspective in terms of the change in flow and in terms of flow scenarios, future flow scenarios. So what if they come and they develop and construct a new dam? What is going to happen to the flow? And the hydrologists then go and manipulate the flow and bring in the future hydrology. And then we can at least see how the inverts and the fish are going to respond to that flow using that data from this 2D model and the 1D model, in fact, using that HAB flow. So it's not just EWRs, but it's also very useful when we need to interpret consequences to scenarios. Thank you.
Yeah, thanks, Kylie. And yeah, maybe just a few concluding remarks. I hope that the slides and the presentation help paint a picture on how all of these different aspects come together. And you can see how measurements and modeling are linked and how it's used to improve management. And yeah, I think just to summarize the slides, in essence, what you could see is that accurate measurements are definitely required to improve water management, like Kylie saying with the black fly situation. And yeah, like Trevor was showing, with the traditional survey and monitoring techniques, there are some safety, time, and cost barriers. However, it is possible to use modern technology to use modern technology to actually improve your depth and velocity measurements, particularly for rivers, and to also collect data related to water quality and discharge. And yeah, in essence, if you do bring together all of these different hybrid modeling techniques, you can improve your results. You can inform eFlows or environmental water reserve studies, monitor your water bodies like your rivers, dams, canals, and improve your modeling and decision making in the long term. And yeah, I think like Kylie said, and from some of the examples you have seen, that it's directly linked to the spaces where agricultural engineers work. So it could be downstream of a dam, upstream of abstraction works for a big irrigation scheme. But yeah, I hope at least now you got a better understanding of how all of the different aspects come together and how the ecology also comes into play with the hard engineering and modeling work. Okay, thank you.
All right, thank you so much for the presentation. Yeah, I just want to say really big thanks, Trevor, Udhav, and Kylie. You guys definitely weren't gatekeeping any information in terms of the methods you guys employed for these case studies. I just got to say it's mind blowing to see the new dimension that all the 4IR technologies bring to the space of engineering and ecology and interpretation in terms of improving the data collection and getting better results from the end of it. I mean, like, just every aspect of it just sort of gets better, from recording to the data crunching to the results, and then even enhancing the interpretation of it. And I'd like to touch on the ecology stuff. I think it's incredibly important, and the relevance is coming through more and more these days. I've seen government departments tightening the accountability of stakeholders. That being corporations and farmers and water use authorities. And even in our own spaces, you see big corporations taking out major bank loans and then obviously requiring environmental studies to be done for their loan applications, and then remedial work that needs to be done in lieu of the assessments. And then on the technology, I think presenting case studies like this are incredibly important. I think by now most of us, we know all the buzzwords from fourth industrial revolution, drones, IoT, sensors, and the like. And maybe even to take it a bit further, we know what they can do, but it's all about marrying that technology, building better models, getting better quality inputs, and then opening more insights from the data based on the results that you get out of it. Right, so I'd like to open the floor to questions from the audience. Senzo, please assist me if you see any things in the chat, but yeah, please raise your hand and feel free to ask any questions. I think okay, we've got a hand up from Prof. Smithers. Please go ahead.
Yeah, thanks. I'd just like to echo what's just been said. I think well done to the GroundTruth team. I think your technology that you're applying is really inspiring. Maybe just a quick question in terms of some of the confidence that you have in the use of the remote sensing technologies. Have you done, for example, verification studies in terms of other methods of estimating, for example, velocity or discharge? Have you done some, for example, some cross sections at river gauging weirs just to see how it would compare against conventional means of estimating discharge, or anything else like that? Thanks.
Thanks, Prof. Yeah, so in terms of the verification, so we use the traditional methods as one way to verify the remote sensing technique. So like a dumpy level survey compared to the cross-section pull from a terrain model that we developed. And then in terms of velocities, generally when we're doing these surveys, we also estimate velocity with flow meters, and if the flows are low enough, we also use a velocity plank. So we generally get more than one estimate of velocity. In terms of discharge for the Olifants River, that was close to a gauge in weir. So we also compared so that was the first time that was actually the pilot of this, and we compared the results that we got from a flow meter, from the gauge in weir, and from the methods that we presented. And yeah, we compared the errors, and we checked errors, and we made sure that our methods were consistent with the traditional methods of monitoring and collecting data. So from the depth to the velocity to the discharge, we did compare along the way, every step of the way.
Thanks.
Okay, I don't see any further hands up. Okay, well, sorry, let me correct myself. Dr. Jumwan?
Apologies.
Go ahead.
Yeah, thank you. Well done to all the speakers. My question is not to the engineers, but to Kylie. I was quite keen to learn a little bit more about the methodologies for determining the flows for environmental reserves. I hope I understood it correctly. So you would probably get a sense for what is existing in a certain river stretch and then try to identify what those flows would be to sustain those ecological habitats. So maybe just a little bit more. Is it just fish and invertebrates, or are there many other things and it's far more complex than what you presented here today?
Thanks, Ashil. That's a great question. So it's more than fish and inverts. It's also so the hydrologists go in, they have a look at the hydrology and looking at the flow dynamics, and they run their various models. We've got the macroinvertebrates. Okay, so like I had separated, it's the responses of the system, which are our macroinvertebrates, our fish. We use diatoms as a surrogate to tell us more in terms of the water quality. So we take samples for looking at the diatoms. As well as then the riparian vegetation specialist that goes and surveys the riparian zone. And then we run each individual model for those different components, and it provides us with that present ecological state for those components. And then we also have a look at the hydrology. They run the hydrology assessment model and the geomorphology, which then runs that model. And they also then establish a present ecological state. So, and then what we do after everyone has now got their results is we do an eco status. This is part of the eco classification, part of the reserve determination before we set EWRs. And essentially we sit around, we plug in the result from the fish only and the macroinvertebrates, and also the riparian vegetation, and we put our confidences into that model. And then it provides us with an ultimate present ecological state, a PES, for that system. And then we discuss what the recommended ecological category should be for that river. And that's where we take cognizance of what's the hydrology looking like, what is the water quality from a physicochemical perspective looking like, and also what's the geomorphology doing, how's the sedimentation, is there a lot of sediment loading taking place, is there a lot of mobilization, etc. So we either, and dependent on anthropogenic impacts and catchment management and the land use around that site, we then decide whether we're going to try and maintain that present ecological state, because we know that the rule within the Water Act is we can't reduce a present state. So if your state is sitting at moderately modified, it must either be maintained or improved. Or if we do see improvements, particularly from a water quality perspective, if there's an upstream dysfunctional wastewater treatment works, we'll key them out and say, right, we'll put some recommendations or mitigation measures to try and see how they can improve, because then ultimately the water quality will improve, and ultimately the biota will respond better to the quality of that system. So sometimes we maintain the PES, sometimes we improve that PES to maybe like a half a category more, so good to moderately modified. And then the hydrologists then take that recommended ecological category and puts it in another model where they then bring out a flow or a discharged, for example, 65 cubics. And that's where we start to play with the 2D model and seeing how the habitats are responding to these different types of flows in order to set that ecological water quality. So when the fish in the invert is happy, we can then set that EWR. But then where the geomorphology and the riparian vegetation specialists come in, and I didn't mention this, so thanks for bringing this question up, is to set floods and freshets. So it's so important for floods to come through a system 2-3 times a year. And then those freshets, those short pulses for 3 days or so, every month or every couple of months, depends on the system. And again, when we're watching that 2D model and looking how the habitats are changing and when that riparian zone is becoming inundated, so if we put in 200 cubic meters per second, for example, we can see that there's going to be a really nice flush through that riparian zone as a flood to reset the system, to get the sediments mobilized, to get those larger cobbles or gravels to move, to scour the system, to remove algae, to clean those habitats that are so important for the invertebrates and the fish. So it's not just based, setting EWRs is not only based on fish and inverts, but setting also floods and freshets, which all go part of the operational plans at the dam, upstream dams, that's where the geomorphology and the riparian specialists come in into play. And again, just to reiterate, watching that model and seeing how the habitats are changing and responding, and which habitats are dominating, and where the riparian zone is under inundation is quite key to setting those EWRs.
Okay, thanks for your response, Kali. I just want to add, we have run out of time. However, seeing how interesting the discussion is, well, let's just give an extension for until 6:10. Let's take one more question from, yeah, sorry, you've got your hand up there. You can go ahead. I'm not sure how to pronounce that. Johag Groex.
Oh, yeah, sorry. I didn't type my name obviously properly, so sorry about that. No, thank you. Quite interesting for me. What was new to me is the water quality that you see in the river and how it changes, which makes kind of sense to me where there's a stream coming from the side that it might be different, but it was interesting that you kind of get that variance almost throughout the river. Is there an indication of how deep you took those samples? Is it on the bottom of the river, or is it on the top, or and perhaps how does one explain those kind of big variances in water quality?
Okay, thanks for the question. So in terms of how deep the measurements were taken, they were around 30 centimeters from the top of the water surface. But we did, that was more, I also see there's a question in the chat box, so I'll answer both simultaneously. It was more sort of a test. It doesn't directly add to the EWR, so it doesn't really inform the eFlows. It was more a test to see if we can collect all of that data simultaneously. In terms of the variations, what some of the key things that could cause those variations, especially with your turbidity and TDS, are like your obstructions in the actual river. There were a few like old trees and stuff lodged along the channel, which visibly were causing problems in the stream. So that was causing eddies and movement within the river, and obviously that linked to your turbidity and your total dissolved solids changing as we did the survey. So yeah, I hope that answered your question. But something else that we're looking into are variable depth. So if needed, going and surveying deeper, so deeper than 30 centimeters. So for the temperature readings, we actually went in 10 centimeter increments. So we did readings at 10 centimeters, 20 centimeters, and 30 centimeters.
Clear, thanks.
Okay, we'll take our final question from Sonke and Sele before closing the Q&A. Sonke, go ahead.
Thank you, Chair, for the question. I think my question is directed to the parts where Udhav was explaining the light, RGB, and imagery sensing. Out of curiosity, do you guys use all the bands from your multispectral imagery, or are there some of the bands that are discarded when analyzing or modeling the water?
Maybe just if I understand the question correctly, so the multi-spec was more to understand the health of the vegetation, so converting it through to an NDVI score. So yeah, that was more the reasoning around the multispectral side of things there.
All right. Thank you.
Yeah, so at the moment, we're not really using the spectral bands to make any inferences about water surface or what's happening in your actual water body, but it is something that we looking into and we will pick up in the future.
All right, thanks.
Okay, thanks for that, guys. I just also would like to add, I think it's incredibly interesting how using water resources management can be an effective for an integrated pest management solutions, as in the case with the black fly. And I think there's certainly more applications. I think about especially in Africa where malaria is a big problem, and acknowledge that water is also necessary for the cultivation, if I can say. But yeah, quite interesting to see what happens in that space further in the future. Right. Just to quickly close off the meeting, I would like to briefly share what's going on within the South African Institute of Agricultural Engineering space. I'll just put up a slide just quickly to you guys can peruse what's going on in the space. But I think just to quickly update everyone is there's a lot going in terms of the industry liaison space. Take for example, like this year, EXA released the identification of engineering works, and we acknowledge that as well, for agricultural engineers, there were certain aspects of agricultural engineering that were left out, and SAIAE as an institutional body, along with the National Council and Executive Committee, have engaged the department and EXA Council as well, trying to rectify that, and also, specifically with the National Environmental Management Act, which is at this point in time prohibits ag engineers from signing off any environmental engineering works in terms of mine rehabilitation. And, we do have a few ag engineers working in that space, and, it'll be a bit cumbersome if they aren't able to sign off any design works or remedial works or reports that they've historically always been able to. Then otherwise, we've got some interesting things going on in terms of the Institute for Electrical Engineers having approached SAIAE to work on some collaboration things to go on. So interesting things to come. We've also got the SANCOLD conference happening in November, as well as the PSAI conference happening in Morocco. So SAIAE just assisting both those institutes with various secretarial and administrative tasks. And then briefly just to talk on upcoming and ongoing SAIAE activities. They're up on your screen, but the big ones being we've got a second season of the podcast initiative coming up. I think the first season was very successful. Great way for everyone to get in touch and see what it is exactly that different agricultural engineers do within their spaces, and also to see how the kind of variety that they exist within our discipline. So the other big thing is the UKZN 75th Agricultural Engineering Anniversary event that's taking part this October. I believe registration is still open for that event. And then in closing, we also have our final meeting for SAIAE KZN as the branch, which will be the AGM as well. Planned at this point for the 28th of October at the Ukulinga research farm at UKZN, and further details to follow in the coming weeks. All right, I think there's nothing further. I'd like to close the meeting there. Senzo, is there anything just to add before we close?
Nothing from my side, Chair. Thank you so much.
Okay. Once again, thank you so much to the presenters, and thank you everyone for making the time today. I hope you enjoy the Heritage Day holiday tomorrow. Please take care. Goodbye.
Thanks, Ewan. Cheers, and bye.
Thank you. Bye.
Thanks, everyone. Thanks for the opportunity. Cheers.
Thank you. Bye.